Hi, my name is Mikołaj Sacha, and I'm a member of Group of Machine Learning Research at Jagiellonian University, Krakow, Poland. I would like to present to you ProtoSeg, an interpretable semantic segmentation with prototypical parts. Semantic image segmentation is the task of labeling each pixel of an image with a corresponding class. It is useful particularly in areas such as autonomous vehicles or medical image analysis. However, most current methods lack interpretability of the predictions, which can be useful especially in high-risk areas. We introduced ProtoSeg, a model that performs segmentation by finding prototypical object parts. Object parts can be compared to prototypes that were found on the training set. For example, bus can be represented as its parts, such as windows, tires, or doors. The architecture of ProtoSeg is inspired by ProtoNet, a model that was introduced for image classification. ProtoSeg consists of a backbone network F, which can be any image segmentation network. However, instead of predicting class scores directly, we first predict feature vectors for each of the pixels. Then, in prototype layer, we compare each of the feature vectors of each pixel to feature vectors of prototypes. There is a predefined number of prototypes for each class, but feature vectors of each of the prototypes are learned during training. In the final fully connected layer, we sum up similarity scores for each pixel and each prototype to get scores for each class for each pixel. This allows us to get the final segmentation map, and also allows us to get activation maps of each of the prototypes for the image. We also introduce a novel prototype diversity loss. Adding this loss term during training ensures that different prototypes of same class correspond to semantically different object parts. In our experiments, we found out that adding this additional loss term increases both interpretability and accuracy of the model. Our experimental setup consists of using DeepLab v2 as the backbone, which was pre-trained on ImageNet or COCO tasks, and evaluating it on two benchmarks, Cityscapes and Pascal VOC 2012. We show in our figures that ProtoSeg allows for a segmentation map which can be interpreted by using activation maps of different prototypes. For example, we can interpret why the model chose such segmentation map for this cat by seeing activation maps for prototypes that represent different semantical object parts, such as nose or outer parts of cat's body. We also can use these object parts to segment image into different object parts, which can be interpreted by comparing them to prototypes in the training set. We show that introducing ProtoSeg gives us a new level of interpretability. However, this also gives us a slight decrease in accuracy when compared to the baseline methods. On Pascal, we have accuracy which is about 7% less mean intersection over union score, and on Cityscapes, it is about 3% less mean intersection over union score. We also experiment with using different backbone architectures. We use UNet as the backbone architecture and evaluate it on another task, which is image segmentation of microscopic images. In conclusion, in this work we present ProtoSeg, a model for interpretable semantic segmentation with prototypical object parts. We introduce a novel prototype diversity loss that ensures that prototypes are diverse, and we show the interpretability of the model predictions using standard benchmarks. Future work areas include improving the precision of the model, applying it to different backbones, and to other segmentation tasks. Thank you for your attention.